recording, so we won't be in, FERPA violations and all that kind of stuff. So have you had a chance to see if you have access to M+? I heard from a couple people that they did not, but then they ended up being able to fix it by updating the Citrix software thingy and then restarting it. Was that the gist of it? There was 2 folks, I think, that I talked to about that. Yes. So if you don't see M+ in the virtual desktop when you do try it, then try to update your software to the most current version and refresh it, and then hopefully that will work. I also fixed the dead link to how to get started using the virtual desktop in the first place. So if you've never had to do this before, this is a handout with screenshots that will walk you through the various steps in getting there. And then I have a video that I had recorded last time on getting started with M+. It's equally applicable now, so I decided just to keep the same video, and there's some example files that it walks through. So this is where you can get a chance to get yourself familiarized with the software a little bit ahead of time. We will look at all kinds of code and output in this class, but I don't run things live. I will build handouts that have the code and the output and lots of annotation. That way you can focus on understanding what the code and the output is telling you, rather than like trying to follow along and run things as we go. So I have these external resources for that. Okay. All right. Anything I'm forgetting or screwing up already? Okay. All right then. What do you remember from last time? Here's a picture to help jog your memory too. I will accept words, letters, gestures. I would accept pictures if you can figure out how to do that.
Like the whiteboards, like in K-12 classrooms, you would hold them up.
Yeah, I could. There is a whiteboard thingy on the Zoom, but it's I'm not good at drawing, so I could do that. What's this class about? Here, nobody wants to look at my purple slides. Let's look at the beach. How about that? What's this class about?
It's about, like, there's something going on that we think is causing other things, but we can't measure it exactly, so we're figuring out, like, how to measure it even though we can't measure it.
Yes.
And looking at how it impacts other stuff.
Yeah, so there's this thing that we believe is there, and we think that thing causes other stuff to happen. And we're using the other stuff as evidence of the thing. Is that close to it?
Yep.
Yep.
That's what I was trying to say.
That's what you're trying to say, yeah. In a nutshell, yes. So these are statistical models that are designed to help us understand how item responses relate to each other, and whether the way they relate to each other is consistent with the idea of there being a thing that caused all the answers. And I say cause in like a theoretical sense, not in a like causal inference kind of sense. Like theoretically, this is how it's supposed to work. Give me some synonyms for the thing that is causing the stuff. Latent factor. Okay, there's one. Latent trait. Latent variable. There's more latents. I'm up to 3.
Can we just do latent with an asterisk at the end of it? Like a Boolean search?
You could, except that actually means something else. Y star is a pretend underlying variable that gave rise to binary or ordinal observed variables. That's actually like a separate thing. But otherwise, yes. So latent variable, latent const... No, I didn't do that one. I gave it away. Okay, latent... Damn it. Latent construct. There's my 4th. What's it called in the IRT class? Anyone who's had that before? Theta. Like, yeah, the latent trait is named theta. What about in classical test theory? True score. Yeah. Am I missing any? Those are the big ones that I can think of. All of those words are getting at the same idea. The thing that you believe exists, and you're trying to measure individual differences on the thing. Yes, indeed. That's what this class is about. So in the lecture we started with last time, I told you about what to expect this semester. Should you be scared? No. Am I scary? No. Am I going to make you take tests? Do you know why I don't make you take tests?
To avoid being scary.
To avoid being scary. We call that construct irrelevant variance. I'm dead serious. Because if I want to measure your understanding of this material, and I introduce another variable into the measurement of that, is that a good thing? Probably not. So then I don't know if you don't know what you're talking about or you're just scared shitless and that your brain is frozen because you're in a high pressure situation, right? So I'm eliminating construct irrelevant variance by making it so that everything you have to do, you can do on your own time and take as long as you need to finish it and get my help, right? Are you to use like ChatGPT to fix your code? No, it will not work. It's really bad at M+. Just trust me on this. What do you do if you get stuck on homework?
If it's more than 10 or 15 minutes,
Yes,
email you.
email me. Yes, if you're fighting with M+, and you get error messages, they're not going to be helpful error messages. They never are, right? It'll tell you some weird thing, and you're like, what the hell does this mean? And I'll be like, oh, that means you have the names at the top of your data set. Seriously, you can't have names at the top of your data set, and that's an error that you will see. So there's lots of those. So yes, those are the other high points. And you should start hunting for some data. That's the other thing. So you don't actually have to have the data in your possession until March, but having a trait or a scale in mind that you're going to be working with would be a good thing. And for those of you who are building scales, like if your lab has created a new measure and you don't have any information about it, that is still okay. You can still do all of the homework one about it. You can tell me as much as you know about what you have and what motivated it. So, and anything's fair game. Let me know if you want to talk about whether your idea for data will work eventually. Okay. Then, so different latent trait models. This class is going to cover measurement models that go by specific names as a function of what type, let's go with this one, what type of outcome they are. So we're going to start with measurement models for latent traits that are predicting continuous responses. That is called confirmatory factor analysis. Once we switch to predicting binary, ordinal, or nominal responses, categorical outcomes broadly construed, that is known by two different names. One is item response theory, and it's not a theory anymore that regression is a theory, that's just what it's called, IRT for short, or item factor models or item factor analysis. These are two different versions of the same model. One is a rearrangement of the parameters of the other. Traditionally, they differ in how they're estimated as well, but I'm going to teach it from a coherent perspective of both. I do have some examples that I think we probably won't have time for, but I'll put them up, of count outcomes, zero inflated outcomes, and other kinds of generalized models. So any kind of behavior or outcome variable that you have that is thought to represent someone standing on a trait, thought to be caused by their trait, is fair game, not just continuous responses. All right, so we started talking about a little bit of history. This is the boring stuff. Talked about classical test theory a little bit. The thing about classical test theory is that T is an idea. All we have, though, is Y total. The idea that your best guess as to someone's trait comes from summing the items that they answered. That's the idea. And the problem with this is that it doesn't give you a way to grow. Oh. I am recording, but I'm not screen sharing. Zoomers, what am I doing? It's like, hello, I've been on Zoom for 3 years and I forget the screen share. Sorry about that. I'm on slide 15, but I'm also not really, I'm just sort of waving my hands and going back and forth yet. I am recording, let me double check. Yes, I am. Thank you for the reminder. Okay, sorry, very bad. I am out of practice at teaching, that's what I've learned. This whole momentum thing, I think it applies to this too. I don't know what day it is, I don't know what time this class is, I don't know what I'm doing. All right.
You'll get momentum.
I need some momentum. I need something a little stronger than this, I think. All right, we're going to do it. Okay, so here's where I was. The idea that your trait is the sum of the items is problematic because you don't have a separation of person characteristics from item characteristics. If your sample of people does really, really well on a test, was it an easy test, or are they just really skilled at what you're measuring? Don't know. What if you want to change your measure to make it more sensitive for people of higher abilities, right? Like you want to extend it. Let's say that you have a measure that's designed for elementary school children and you want to be able to measure junior high kids, right? Well, it's not the same if you have to change the items, then you can't compare. So the drawbacks of this in practice is that we're assuming without testing that adding the items together is cool because there's only one trait that's creating them. That's an assumption that is testable. And we're also assuming that all of the items are equally good. And that's probably not the case, especially for social sciences outside of education, where the items are like sentences that people write that vary in a lot of different ways, not just math problems or vocabulary problems or something like that. So I think this is where we left off, I think. Does that sound right? Cool. Picking up on slide 18 then. All right, so confirmatory factor analysis then, our first foray into latent trait models. The idea is that the indicators should go together to measure something, and what the extent to which they're going together in a way that is consistent with one thing versus two things versus three things is a testable hypothesis. And the confirmatory part is really important. All of the models that we're going to look at in this class are confirmatory in nature. Exploratory factor analysis is not a model. So this is not something that I'm going to spend time in class on. I posted material on this topic that you can take a look at as your time permits. It fits in terms of your textbook before CFA, but I think it might actually make more sense after we get done with CFA, because then you can see what the constraints are. But in exploratory factor analysis, you let the computer figure out how many factors you have and what they should be called based on which items relate to those factors. And the reason that it's not a model is because one person could look at a set of output and say, I think there's 3 factors, I think this is what they mean, and I think this rotation is the best one. And someone else could say, no, there's 4. There's 4, and this is what they mean, and I like that rotation instead. Who's right? They both are. There's no standard by which to evaluate who is righter than the rest, and that's why I don't like it. There is a common misconception, I think, that in order to do confirmatory measurement models, like you have to have a really strong theory or evidence to fit it. No, you have to have a clue. Just a clue. I guarantee you that if you're part of a scale development team, you spend a lot of time thinking about the items and how to measure the traits that you have and what traits they are and how they should be measurable. So all you have to have is a clue to start with. The beauty of these models is that you get results that guide you to why you might be wrong, where the problems are, where there is a mismatch between if your model was right, what the data should look like and what they actually look like. And that mismatch is informative. So confirmatory models is where we're at. So why do we use these? To provide separation of persons and items, as well as any other sampling dimension. So this is commonly stated as a benefit of IRT specifically. It is not. It is a benefit of any kind of measurement model that has a latent trait that is separate from the sum of the items. Anytime you separate the items and persons via a separate variable, then you have those benefits. A lot of people use CFA to analyze ordinal responses. So most social science research that I've seen has ordinal response formats between something like strongly disagree up to strongly agree, or how often do you do something, never, occasionally, blah, 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 blah. Ordinal is a very common response format. The best you can do with CFA is have it be not that wrong for ordinal. It's not designed for that. There's a lot of research asking when it's normal enough to use CFA. And the rule that people often like to state is if you have at least 5 choices, it's fine. It's not ordinal anymore. That's not true. It depends on how people use the 5 choices. So if you're looking at a trait that is not likely to have a lot of people on the high end or the low end, like if you have very skewed response distributions, some of you are looking at criminology, I heard. There's externalizing last time. There are a few others where you're hoping people are low, right? Like ideally, if a child is healthy or someone has good mental health, they would answer never to how many times do you do these maladaptive behaviors, right? If you have a pile of nevers and a tail off after that, that's not going to lend itself to assuming that that variable is continuous, because the model is going to want to predict something lower than never, and it can't. So there's boundaries that we have to obey, and that's why CFA is not ideal for that situation. But that's where we're going to start, because it's still very common, and the logic of it is the basis for doing ordinal measurement models instead. So this little thing right here is a linear regression equation. In this class, I stands for item and S stands for subject. So the response to each individual item per subject is a function of an item-specific intercept plus an item-specific slope times the predictor x, which is a subject characteristic, plus some item and subject-specific error, right? Other than the subscripts being 2 instead of 1, this is a linear regression equation, right? Yeah, it is. So is this. Except we got to change all the letters. I didn't make this up. So my outcome is the item response in these models. So the behaviors, the answers to the questions, those are your outcomes. So it's a multivariate model. We're analyzing all of them at the same time. So this is one equation that's meant to summarize a series of equations where each separate item would have its own equation. So response y to item I for subject S is a function of this mu-looking thing here. That's an intercept. Each item gets their own. What's an intercept? The constant, yes. In this class, this is a constant, and this is also a constant in the sense that it's not a variable. But mathematically, what's an intercept?
The line crosses the y-axis.
Mm-hmm.
So it's your y when all of your other variables are 0.
Yep. Y, it's your predicted y when all your other predictors are 0. That is still true in this class. This is your expected item response for somebody who has a factor, f is my predictor, of 0. In your textbook, they use squiggle 1, one of the Greek letters that I can't say or draw, for your factor score, and I'm not here for that. It's f for factor. So f here is my predictor. That's my latent trait. So I'm writing this model as if I know what f is for each person, but I don't. That's the crazy part. F is technically treated as missing data. We don't know what the factor scores are, but we actually don't need to make all of this work. Each item gets a slope, lambda. This is known as a factor loading. It's a slope. What's a slope? Zoomers, you can play along too. What's a slope? Not a trick question.
The amount your predicted variable changes based on the degree of x you have.
So if I told you my slope is 2, could you put that in a sentence?
My y value would increase by 2 for every 1 point increase in x.
That's it. This is a slope. It means the same thing as usual. The only catch is that the variable that it's multiplying doesn't exist. I know, it sounds crazy when you put it that way. If I have a good item, do you think my slope should be big or little? If my item measures my trait well. Big, yeah. There should be a strong relationship. As my trait goes up, my item response should go up. And it's almost always positive, by the way. We always recode things so that they're all headed in the same direction, otherwise the model gets confused and doesn't know which way is up. If my item does not measure my trait, if it's a crappy item that has nothing to do with the construct, what do you think my loading's going to be? 0. Yeah. And if something went really, really wrong, this could go negative even. And yes, I've seen that happen.
What does that mean?
Because ideally, all of your items would be related to the trait in the same direction, or you would recode the responses if it were measured opposite so that it's consistent. So a negative loading would mean that as your trait goes up, your response goes down, like it's backwards. This is called discrimination as a construct, and it's a empirical way to answer the question, is each item actually doing what it's supposed to do? And you can compute effect sizes the same way you would in a regression model for the strength of this relationship. What about E? What's this got to be? Error? Residual? It's whatever else is causing your answer. So just like in regression, we don't need to know what the E's are per item per person, but we estimate their variance. So each item is going to have an error variance as well. So usually in CFA models, but not always, each item is designed to measure one trait at a time. Sometimes there are sort of extraneous traits that end up showing up. So for instance, if you're measuring externalizing behavior, we'll start with that, and you ask a parent a bunch of questions about a child and you ask their teacher the same questions. Odds are good that the responses from the same person are going to be related above and beyond just that they're measuring that same kid. So then you might end up with a second factor that has to do with who answered the question beyond just the externalizing latent variable that you came here to measure. But this type of model assumes something called local independence, which means that the residuals are unrelated. The only reason that the outcomes should have been correlated in the first place is right here because of the factor. And what's left over should be unsystematic. That's another testable assumption. To the extent that there's correlations left over, you do not have one trait. You've got more than one. The extent of leftover correlation can help you figure out what those extra stuff might be. It's a linear model. So as the factor continues to increase, y continues to increase. Now, if I have an ordinal response format, 1 to 5, my model will predict an answer of 6 or 7 for really high trait people. It might predict an answer of -1 and -2 for really low trait people. That's a problem. So that's why confirmatory factor analysis is not ideal for most common response formats that are ordinal. By the way, ordinal has to have a special name in these models. It's polytomous. I've heard of polytomous IRT models. You gotta just make up names. That's the crazy part, is that we have the CFA unit, and then we're gonna talk about the exact same things with all new names and all new terminology and all new notation. It's nuts. But it is job security. I'm dead serious. When we get to IRT models and M+, one of the parameters is going to have $signs in it on the output. I shit you not. I'm not, those of you who've run these models before, am I making this up? I'm not making this up. And I always make the same joke, that's the money symbol, because if you can learn this stuff, someone will pay you so they don't have to. There's literally $signs on the output. They're thresholds, by the way. So in this framework, because items each get their own slope, now items are not assumed exchangeable. We know specifically for each item how well it relates to the trait. But because the slope is linear, and a linear slope keeps going forever and ever in both directions, we assume that the item is equally good across the range of the trait, a linear slope. But that can't fit ordinal outcomes. It has to shut off as you get towards the boundaries. So that's the translation of this type of model, a regression model, into ordinal or binary data, is we're going to take the model and make it so the slope shuts off. For those of you who are like, if you're thinking, is she talking about logits? Yes, I am. Yes, I am. And that's why it's helpful, by the way, if you haven't been in the generalized linear modeling class, or you're not in it right now, to review that unit from it. So I have that linked a couple of different places, I think, on the syllabus, as well as in this lecture. The logistic regression section of that course will be very helpful to understand how this model translates into an IRT model through the magic of logit link functions. And the timing works out that if you're in both classes right now, we'll cover that well in advance of getting to IRT, so it works out well. Okay, so then we get through the history of factor analysis being developed for purposes of measurement. So people used to fight about intelligence and whether intelligence is multidimensional. In order to have that fight, they had to invent factor analysis so they could see how many factors underlie performance in intelligence tests. I'm not going to weigh in on that, but I think it clearly has to be. Then we get into more of this thing. People are coming up with ideas that they couldn't necessarily implement. So like the theory was there before the computations. The first structural equation modeling program was Lisrel, invented in the 1970s. It was specified entirely using matrices, not making it up. Apparently, it was so difficult to use that the people who learned how to use it were called Lisrelites. Not making it up. I heard that from one of my person who taught me SEM. So it's come a long way. There's a million different SEM packages, and they're much easier to use nowadays. And you will be surprised at how straightforward the syntax is to be able to do these things. So I give you these dates on here, not because I need you to know a full recollection of all the history, but just to look at how not new this stuff is. So modern measurement is not really that modern. So this was one line of research that worked on factor analysis from the perspective of psychology and measurement of intelligence and and personality and other things where people are arguing about how many factors go into personality, big 5, big 6, et cetera, et cetera. On the other side of the pond, though, was separate research focusing on the prediction of binary items, which was necessarily different. So IRT came about separately based on physics, actually, and the earliest writings about that were in the 1950s and 60s. So the thing about IRT is that it looks completely different as a model. It looks nothing like regression or any linear model that you're used to, but it is. And that was where the connection came from, of people figured out how to make them look like the other, and then people finally realized that these are the same thing. So the linear regression model that I just showed you for CFA is to confirmatory factor models, as logistic regression is to binary factor models, which are known as IRT. So it's the same trait, and it's still going to be an F. I might call it a theta. You'll hear me switch terminology, but it's the same idea. I have a predictor that is a continuous latent trait, and it's predicting item responses. But I have to change how it's predicting it because the responses are not continuous. So you can think of IRT as a generalized model, and that term in particular usually goes with the type of estimation known as full information maximum likelihood. Whenever you see this term here, full information, what that means is that it uses all of the original data in estimating the model. That's usually what happens. But because that is very difficult to do in IRT models with multiple traits at the same time, what we will also get a chance to practice is something called limited information estimation. And in that approach, it starts by making a summary of the data. It summarizes these into a special type of correlation matrix, and then it fits a CFA model on that correlation matrix. In IRT land, there's a term called a Roche model that's named after a person, and that is a very different viewpoint. So the way that I was taught is like, well, a Roche model is just an IRT model where you set all the slopes to be equal. And the Roche measurement community would not be happy with that description. So we will see more about that later, but if you've heard this term before, know that this is within the same ballpark. It's a constrained version of an IRT model. So people do this to analyze categorical outcomes, binary, ordinal, or nominal. Sensitivity of measurement across the latent trait. So this is the idea of an item being not necessarily good for everyone, but good only in a certain range. And it provides separations of persons and items, as in CFA, because there's a separate trait and not just the sum. So let me show you some pictures. Aren't these pretty? They're lovely. So this type of picture is known as an item characteristic curve, or ICC for short. And if you're like, hey, I thought ICC was the interclass correlation. It is. Sorry. We reuse things all the time. So in this plot, this is showing an example of predicted relationships between theta, the latent trait and an ability, it's often called in an educational measurement context, but it could be depression or externalizing or criminal whatever, biological whatever. I heard too many examples today, now my head's full. And on the y-axis is the probability of endorsing an item or getting it right. So this is a binary item picture. So probability is bounded. The model understands that. The magic of generalized models and logit and probit link functions is that it makes these lines bendy so that they stay within bounds. These lines differ in 4 features, which will be item parameters. We're usually going to use 2, but in these asymptote ones get used in special cases. So first up is, now note the cleverness of these names, A, B, C, and D. I'm not making that up, that's what they're called. Certain authors, by the way, flip A and B, and when they do that, my head just explodes. I can't take it. Sometimes D becomes an intercept too, that's another one. But A is discrimination, it's a slope. So for instance, the pink line here is steeper in slope than the blue line. Pink wins. However, pink doesn't win all the time because difficulty or severity, as you can think of it in a more psychological context, is where the line is relative to the ability continuum. And more specifically, in these models where you only have A's and B's, difficulty is the point where the line crosses a probability of 0.5. So the green line here, this green line has greater difficulty in terms of its item characteristic or greater severity. The green line is optimal for measuring people who are high on this trait. If somebody is low on this trait, I don't have any idea what they're going to answer. Probability is 0 for like the entire lower half of the distribution, whereas this blue line right here is the opposite. It's designed to distinguish people of lower trait levels and not so much the higher part. So a consequence of the lines getting bendy to make sure that they predict things within the boundaries of the item response format is that an item is no longer just good or bad unilaterally, it's good or bad in certain parts. So if you're interested in measuring only high ability people, you probably don't need some of the items that top out over here. If you're interested in only measuring lower people, don't give them the green item, it's not going to help them. And if each item is only useful for part of the range of the trait, then guess what happens to reliability as a construct? How well does this test work? How accurate is it? The answer is going to depend on where you are on the trait. It's the match between subjectability and item difficulty that matters in these models. Questions?
About difficulty, so in this case, are both the green lines and the bluish line, would those both be considered difficult, even though they're at different ends of the ability?
So this continuum is easiness to difficult.
Oh,
So it ascends in difficulty. And the blue line crosses the 50-50 mark at a theta of about -1, whereas the green line doesn't cross it until a theta of about 2. So the green one is much more difficult. Or severe, like you can think of these in that continuum too. Like if you're talking about behavior problems or something, then like this would be, setting the neighborhood pet on fire. as opposed to, fighting with your parents. What?
So in the case of that dark blue line, since it's starting at slightly over 0.3, would we still treat that 0.5 mark as difficult, or we look halfway between 0.3 and 1?
When there is thank you. When there's a C parameter, it's not exactly 50.5. It's influenced by where C is, but the idea is still the same. It's like where it is in this dimension is difficulty or severity. So yeah, that brings us to C as a potential add-on. This is really only relevant in, I think, an educational testing context in which you have a multiple choice item and there's some chance that you're going to get it right just from guessing. So lower asymptote is just what it sounds like. It can be estimated per item to describe the bottom probability, no matter how low of a bill you are. So if you have a 4 multiple choice item, C might be 0.25. Like, probability is not going to go below that. Where you would end up with different C's is if you have different differentially good distractors, right? If one distractor is really bad, like no one would ever pick that, then they have a higher chance of selecting the right answer. Less commonly, but it does exist in certain contexts, is an upper asymptote. And that taps out so that you don't end up at a probability of 1. And examples that I've seen of this, some people call it like carelessness. Like even if you're super high ability, there's still some chance you're going to screw it up. So probability is not predicted to be 1. This could also be, again, in the case of like psychopathology, somebody who knows enough not to give their true feelings, right? So if you plan to set the neighbor's cat on fire or something, right, are you going to admit that? Probably not. So there's some chance that people who should endorse something are not going to because they know better or there's something else at play. So like where the line tops out can be a parameter, where it bottoms out can be a parameter. But A and B are generally what we would focus on in a non-educational measurement context. Okay. And yeah, okay, almost there. Like 2 or 3 slides and we'll be done. So this is the model. I have link here, which is going to become a transformation of probability that makes it so we can predict it as a continuous variable instead. A, which is item discrimination, it's like a slope. Here's my theta, that's my factor for my subject, minus B. So this equation looks nothing like a regression model, especially the minus sign. The minus sign is used so that difficulty goes the right way, and higher scores actually mean more difficult and not easier. Otherwise, it's backwards. This is what it looks like. Can you just trust me that this is still a regression model? And I'll prove it later. And I mean like prove it in the math way, like I'll show you how to get back and forth. Okay, I promise. This version of the model to me is actually more useful in understanding your items than the regression version, but you can get back and forth. So this link thing, this is either going to be something called a logit or something called a probit, but in IRT class, probit is called ogive instead. And if you're like, what the hell is a logit? Yes. I took IRT and the whole time the instructor was like, oh, the model is linear in the logit. And I'm like, well, that's great, but what the hell is a logit? The logit is the log of the odds of the probability of a 1. Why do you need a logit? To keep your predicted probabilities between 0 and 1 where they belong. That's the answer. So we'll spend a lot of time on the logic of that, but that's the quick version. So item factor analysis is the version that looks more like a regression model, but this minus sign is going to make us have a little bit of a headache for that. So items are not all created equal. They vary in their difficulty, they can vary in their discrimination, and that means that they're only optimal within certain ranges of the trait. And if each item only measures part of the trait, then that means reliability can't be a single number. It has to be a function that depends on where your items are and how good they are in those spots. So we're going to indicate reliability with something called test information instead, where it literally is a function and not a number. So then we have the development of all of these models in the 50s and 60s into the 70s. Once again, these are not new things, is the point that I wanted to make with that. So that's the big picture here. is all of these factor models are trying to do the same thing. They're trying to create an empirical way of answering the question, do these items measure one thing or is there more than one thing? And if so, how well does each item measure the thing? Back to where we started. We're measuring, actually, the thing measures the stuff. I think I got it wrong, but it's all right. Okay, so the things that we will learn how to do. Build models for dimensionality. The traits don't exist, right? That sounds like it should be a problem, but we don't need them to exist. Because what we're actually going to look at is the predicted pattern of relationship across the items that the trait would imply. And see how well that pattern that's predicted by one trait matches the data. And then we can see if a pattern predicted by two traits matches better. The difference in how well they match is a comparison of model fit. So then it's not, well, I think there's 3, and I think there's 4, and there's no way to see who's right. There's a p-value. You can see who's right. You get about 8 different measures of how much better one model is than another that we can all report and look at less subjectively. Let's go with that. This also, in the context of IRT and IFA, helps you figure out where you might need more items. So when you have your reliability function, right, if it peters out at one end, you know that you need items on that end. Or if you don't care about that end, maybe you don't need more items. So as a quick example, Vladimir and I last summer worked on a project designed to look at risk for recidivism in people who had DUI or other types of drug or alcohol problems. And they're worried about the people who have big problems, right? These are the people who are going to end up in jail or have other bad outcomes. Their information functions were really low on the low end, where the healthy people were. We don't care about them. If you're not likely to have a problem, we don't need to know how not problematic you are. We need to know how problematic you are if you have problems with a capital P. So that is a very different way of thinking about, like, how many items do you need and where should they be? It's like, no, who do you want to measure? Let's make sure we've got information in that range of the trait. We can make sure that we have comparable traits across sets of items and sets of persons and even sets of occasions. If you do it right, you can change your test over time and still be able to compare test scores. You have to have them overlap. That's the key idea. We'll talk about that too. And comparability across groups. So if you have an instrument that was developed for one population, you'd like to use it on a different population, can you just do that? Or is reviewer 2 going to have a field day with you? Probably. So you need to show evidence that this set of items works the same way on a different population and potentially be prepared to adjust if not. Works the same way is operationalized in confirmatory factor models as examining measurement invariance or measurement equivalence, where measurement equivalence is called, and I'm not kidding, measurement non-invariance. The terminology is god-awful. You can't just say the same. Oh, it's not that it's the same, it's non-invariant. Non-invariant means different? Yeah, that's where we're at. So, yeah, it's horrible. So,
Who can I complain to?
yeah. Is what?
Who can I complain to?
I don't know. I mean, we all hate it.
Your
Like,
own textbook.
yeah, like I'm not the first person to complain about this, but we still just all keep doing it. So when I'm trying to not talk in a technical language, I'll just say, does it work the same way? It's invariant if it works the same way. Then we get into IRT, and it's like, no. We're going to look at differential item functioning. Oh, that's the same damn thing from the opposite perspective, because diff is non-invariance. Again, don't make this stuff up. It's the same ideas, though. The idea is that if you're only measuring the traits, then regardless of what group you're in or your background characteristics, all we need to know is your trait level, and we can predict your outcome. If there's something else in the story, then that's potentially a problem. That is potentially creating bias that you do not want. Construct validity. Internal evidence is something that these models can buy you, in addition to external evidence, which is more like correlations with other stuff. If you understand your construct, you should be able to predict which items are more difficult. The extent to which you're right is evidence for construct validity. So the ordering of items can support your interpretation as this being the trait we're looking at and not some other thing. And you can do this regardless of any kind of outcome, and you can mix and match. So you can have a scale that has binary outcomes, ordinal outcomes with 3 choices, ordinal outcomes with 4 choices, and response time. You can make a trait out of that. They don't all have to match. I know, it's so cool. So yeah, many advantages. The downside, sample size. You need a lot of people to pull this off. And that's why adding items up and calling it a trait is still a thing, because not everybody has large sample sizes that are needed for estimation. So it can be tricky to pull off in practice, and you'll run into this if you try to analyze your own data and you don't have large samples. But there are ways that we can try to simplify the model to make it work better. So estimation is harder, particularly in IRT. Anytime you're combining link functions and latent variables, it's a hard thing. And the stuff is hard to read, except for the stuff I picked, so please read it. I tried to pick articles that were written in English as much as possible, where there's lots of words and not just like symbols. So I tried, especially your textbook. So, and last but not least, these models can't save bad items. All they can do is tell you that they're bad. So there's no magic that's going to happen here. And when we get to SEM, it is not causal modeling. People call it that, but it's decomposition of a covariance matrix. There's nothing causal about it. Cause comes from design. So that part hasn't changed. All right, there. That is a great place to stop. 143. Questions? Thoughts? Okay, we're taking a thumb poll. How excited are we? Still sideways?
More positive.
More positive than before.
It was
Okay.
a little bit down and now it's like.
Okay, we're working on it. We're heading in the right direction with our momentum. All right then, thanks for being here. It's Thursday, so I say have a great weekend. Let me know if you need anything, and I'll see you next week. Bye for now.